Okay, I think we can start. So good morning, good afternoon, good evening to all the attendees. I am Giovanni Rosurdo, and I am the spokesperson of the Virgo collaboration. I'm very glad to welcome you today to this LIGO Virgo KAGRA webinar focused on the presentation of the paper Gravitational Wave Transient Catalog 3, compact binary coalescences observed during the second part of the third observing run. Next, please. And on this slide, you can find a reference to the paper released on the archive. Next, please. So the existence of gravitational waves was predicted by Einstein in 1916, but it took 1 century until they were directly detected for the first time on September 14, 2015. Since then, LIGO and Virgo have performed 3 observing runs, named the 1, the 2, and the 3. The next one of 4 is scheduled to start in 1 year from now with enhanced network sensitivity and also KAGRA joining. The paper we are presenting today collects the events detected in the second half of the O3 run. This paper comes just 6 years after the first detection of gravitational waves, and as you will see, even if the time is short, a long way has been walked so far. This is our third catalog paper, reporting 35 new events for a total now of 90 since the first one detected. All of the observed events are coalescences of binary compact stars, either black holes or neutron stars. Next, please. This is not the end of the story. In the next days, we will be presenting more papers based on the analysis of the data presented in the catalog. On December 9, we will present constraints on the cosmic expansion history from the catalog. Next day, December 10, we'll present the population of merging compact binaries inferred using gravitational waves through the catalog. And finally, on January 20th, 2022, we'll present tests of general relativity with the catalog data. Today with us, we will have a few speakers covering several aspects of the paper. Francesco Di Renzo, who will describe the instruments, Jess McIver, talking about the data, Becca Ewing, talking of candidate search, Isabel Romero Shaw on source properties, and finally, Christopher Berry will be moderating the Q&A session. Also with us, there are several panelists to answer specific questions from the public. So Carl Blair, Loic Roland, Sid Soni, Gareth Caburn-Davis, Frédéric Marion, Eduardo Milotti, Dimitri Estevez, Marek Szczepancik, Trinh Nguyen, Daniel Williams, Sergei Osokin, Meg Milaus, Rosa Poggiani, and Anna Middleton. A brief outline of this presentation, which will basically cover all the aspects ranging from how we detect gravitational waves to how we use gravitational waves for astronomy. So instrument, data, then candidate, sources, and finally the release of the data to the wide community. So I'm happy to hand over to Francesco Di Renzo for the first part of the presentation.
Great. Thank you, Giovanni. Hello, everyone. Next slide, please. So before jumping to the description of the instruments and the upgrades to them that made possible the results that we are presenting today, let me quickly introduce gravitational waves, where they originate and how we detect them. Gravitational waves are ripples in the fabric of space-time. When objects move, or to be precise, accelerate, the curvature of space-time changes, and these changes propagate outwards like ripples on a pond in the form of gravitational waves. One of the most outstanding sources of such waves is, for example, the collision of compact stars, such as neutron stars and black holes, which are the protagonists of this third gravitational wave transient catalog. Then, these ripples travel through the universe at the speed of light, carrying information about their origins and the very nature of gravity itself. Their effect on a circular array of test masses is described by the animation on the right, and corresponds to an alternate stretch and squeeze of the relative distances between the masses. Our goal is to measure the strain and infer the properties of what has originated the signal. Next slide. Interferometric gravitational wave detectors was a simplified optical scheme, as be reported in the figure on the right, are currently the most sensitive instruments devoted to measure the strain produced by an incoming gravitational wave. The differential stretch and squeeze of their arms, like in the animated picture in the previous page, produces a varying amount of light passing from the antisymptomatic port of the beam splitter to the detection photodiode on the bottom of the image. This is the detector output, the observable where to look for the imprint of a gravitational wave signal. Advanced LIGO and Advanced Virgo are the second generation of kilometer-scale interferometric gravitational wave observatory. The two LIGO detectors, located in Hanford and Livingston, started taking data in September 2015, with the first advanced detectors observing run, named O1. Virgo joined them in August 2017 during the second run, O2, and here I'm presenting the most relevant upgrades to this network of detectors in the second part of the third joint observing run. The detector performance was similar to in O3A, where the main improvements with respect to the previous observing run were the adjustment of in-vacuum squeezing for the two LIGO detectors and an increase of laser power in Virgo. Both these interventions aim at increasing the detector sensitivity at high frequency. In the case of laser power, the higher the power, the smaller the fluctuations in the number of photons arriving at the detection photodiodes. That is the so-called shoot noise. Quantum squeezing is instead a technique to produce a vacuum state of light that has uncertainties in amplitude larger than those in phase with respect to a normal vacuum. The reduced phase fluctuations provide a better detector sensitivity at a high frequency. The main improvements after the 1-month commissioning break preceding O3B comprise adjustment to the squeezing subsystem and the reduction of scattered light noise for both LIGO detectors, and also the implementation of the reaction chain tracking, which will be described in further detail in the next section. Virgo improvements include a further increase in the input laser power and the improved electronics of the detection photodiodes, which reduce the noise at low frequency. Moreover, adjustments have been also done to the ettalon feedback system, which controls the residual symmetry of the detector arms produced by the cavity created within the two surfaces of the input mirrors, and their changes with temperature, that is the so-called ettalon effect. Other improvements include better alignment, which reduced the scattered light, and software improvement to the storage of some channels used for the strain reconstruction. Overall, this adjustment produced a significant increase in detector sensitivity, as I will show in the next slide. Let me comment on the figure on the right, describing first how we can measure the detector sensitivity. This quantity can be characterized in the frequency domain by the amplitude spectral density of the calibrated strain output of the detectors. This gives a measure of how sensitive we are in the frequency domain to an incoming gravitational wave signal. Any signal that is larger than these curves can be detected, and a single quarter will not be observed. The representative O3B strain sensitivities are reported in this figure for the LIGO Hanford, LIGO Livingston, and Virgo detectors. Another important quantity to describe detector performance is the duty cycle, that is the fraction of full operating time of these instruments. This duty cycle was pretty good during O3b, despite the winter season and the associated period of bad weather condition. Overall, we have had a total of 142 days with at least one detector observing, and 85% of the total O3b duration with at least two detectors, which is even better than what we achieved during O3-8 and the past observing runs. Next slide, please. Okay, let me introduce another figure of merit to characterize detector sensitivity, which is directly related to the number of detections that we can achieve. This is the detector binary neutron star range. Binary neutron stars are a class of sources whose spiral signal is very well characterized, and the average distance over orientation and sky position at which a detector can detect them provides us a metric to characterize detector sensitivity, as well as the expected number of achievable detections. In this page, the left-hand side figure represents the evolution of the BNS range for the LIGO and Virgo detectors. The dashed lines are the median ranges of O3A, and the epochs marked on LIGO Hanford and Virgo plots represent significant improvements in sensitivities. The right-hand side plot describes the distribution of the range and their median values for the entire O3b run. Notice here that the distribution of Virgo data is bimodal as a consequence of the interventions on the detector implemented at around January 28, and highlighted by the two shades of purple in the distribution. Not evident from this figure is the contribution to the detector performance after the implementation of reaction chain tracking in the two LIGO detectors, which will be described in the next section. And now it's time to turn it over to Jess to talk about calibration and data quality. Thank you, everyone.
Thank you, Francesco. So I'll discuss the data we use to produce the results that we're presenting today, and I'll next touch on data calibration, which converts the raw output of the detectors that Francesco described into gravitational wave strain data used for all of our astrophysical analyses. So to produce a final version of calibrated data, we make use of an improved understanding of the behavior of the detectors in their local environment. So this process can take months at times. And following the same procedure as previous event catalogs, the calibrated in this latest catalog employed noise subtraction. And we can see an example of noise subtraction in the figure on the right. So this is from the GWTC 2.1 paper, which shows strain data for a LIGO detector. Amplitude of the strain data is on the vertical axis and frequency is on the horizontal axis. And the red trace shows strain data prior to noise subtraction. And you can see strong artifacts near 60 Hertz from the US power grid. And the blue trace shows strain data after the application of our most sophisticated noise subtraction. We used this noise subtraction, illustrated here, for all of our paper results in the GWTC3 catalog, except for coherent wave burst, or CWB. So this analysis used a slightly different version of the calibrated data, but both versions of calibrated data are available on the Gravitational Wave Open Science Center, along with documentation on the different noise subtraction methods applied in each version. So you can learn more about the general calibration procedure for both LIGO and Virgo from the references on the lower left. Next slide, please. Data quality is another key data product for astrophysical analyses, and we'll start with the glitch rate at each detector. So the glitch rate is a key metric for informing searches for gravitational waves, and glitches are short duration bursts of noise in detector data that can mask or mimic a true gravitational wave signal. And the higher the rate of glitches in any one detector, the higher the chance that glitches could coincide by chance at more than one detector and produce a false candidate signal. And this is especially true for glitches that have a similar morphology to gravitational wave signals that we're searching for. And you can learn more about glitches in gravitational wave data from the reference in the lower left. The figure on the right shows the glitch rate for each detector during the O3b analysis period. The vertical axis shows glitches per minute, and the horizontal axis shows time, so both in days from the start of O3b at the bottom and months at the top. And each point you see is the average glitch rate for that minute, and the continuous curve is a daily median. And we also show here some dashed horizontal lines. So these are the average glitch rates for O3b and also for previous catalog analysis periods, so O3a and O2 for each detector. And I'll highlight some interesting features, starting with the Virgo detector in purple. So overall, Virgo had a slightly higher glitch rate in O3b than O3a, and this is largely driven by spikes in the glitch rate related to bad weather, as Francesco was describing, and this is associated ground motion. And the LIGO detector glitch trends are similarly driven by ground motion, and we'll get a better sense of the major O3b glitch culprits on the next slide. So the new plots on the left are showing the time frequency morphology of some of the major drivers of glitch rate at all three detectors, this being different forms of light scattering. So frequency is on the vertical axis now, and the horizontal axis is time, here on the scale of 4 seconds. And color is showing the normalized energy of the data. And slow scattering, which you see at the top, is caused by a modulation of the phase of the light circulating in the detector by some moving surface. And slow scattering was particularly prevalent at the LIGO Hanford detector during O3b. On the other hand, fast scattering at the bottom has a similar underlying mechanism for coupling into our strain data with an additional modulation that gives it the distinctive pattern that we see here. And fast scattering was particularly prevalent at LIGO Livingston during O3b. And in the middle of O3b, commissioners at the LIGO detectors reduced, as Francesco mentioned, reaction chain tracking, or RC tracking, as shown in a vertical dashed line in the glitch rate figure on the right. And this reaction chain tracking minimized the motion of the optics that are responsible for circulating light in the detector arms, and it minimized their motion relative to components of their suspension system. And the introduction of this RC tracking significantly improved slow scattering at both LIGO detectors. And correspondingly, we can see at LIGO Hanford that the average glitch rate drops, corresponding to a decrease in slow scattering glitches after this change. But RC tracking did not have as much of an impact on fast scattering. So at LIGO Livingston, the glitch rate still follows weather patterns, and you can see it actually rises a bit after RC tracking is first implemented, and this is due to high ocean wave activity. So you can learn more about light scattering and gravitational wave detectors in the reference in the lower left. Next slide, please. So once candidate events are identified, we next validate them by checking for evidence that they were caused by one or more detector noise artifacts, following the same procedures that we used for previous catalogs. And here are the major results for our paper. So no candidates in the GWTC3 main event candidate list, which Becca will discuss next, were found to be likely instrument artifacts. However, 3 candidates in the marginal event list were found to be likely due to noise. So these are marked in our GWTC3 catalog paper with an asterisk. And I'll wrap up the data discussion by summarizing data products for source property estimation of candidate events, which Isabel will discuss in about 15 minutes. And in cases where gravitational wave candidates overlap or occur in close proximity to glitches, we model these glitches and subtract them from the strain data before we analyze them further. We use the Bayes wave algorithm for glitch modeling in cases where we don't have an auxiliary sensor that witnesses the noise. And this is an iterative process that can take months. And on the right, you can see an example of glitch subtraction for a neutron star black hole candidate. So this is GW200115. And these time frequency spectrograms show 40 seconds of data. And original raw data is on top for a LIGO detector, and glitch subtracted data is on the bottom for the same detector. And you can see the signal track of the candidate in orange. And the neutron star black hole discovery analysis used the raw data at the top and an analysis cutoff of 25 Hertz, where they only analyze data above the non-stationary noise. Our catalog used glitch subtracted frames once they were available and the full frequency range for our analysis. And you can find glitch subtracted frames available in the Open Science Center for all 8 events in the GWTC3 main candidate list that required glitch subtraction before parameter estimation analysis. And this next brings us to searches for gravitational wave signals. And please take it away, Becca.
Okay, thanks, Jess. Next slide, please. So I will be discussing how we search for signals and the list of candidates that we identified. So I wanted to first start with kind of a high-level overview of all the detections we've made in the past 3 observing runs, and now including results from O3b for the first time. So in this cumulative detections figure, you can see that our detection rate in O3b is consistent with what we saw in O3a. And this is just due to the many detector upgrades and data calibrations that Francesco and Jess discussed previously in the talk. So now at the end of O3b, we have added 35 gravitational wave candidates to our cumulative catalog, and this brings our grand total to 90 events. Next slide. So we follow the same search methods that were used in GWTC 2.1 and GWTC 2, and our searches are done on 2 different timescales. So first we have the initial low latency analysis, which is done in near real time as the data from the detectors are being collected. And then later, after the observing run ends, we reanalyze all the data in what we call an offline configuration. And it's the results from this offline reanalysis, which is a more sensitive search, that we include in this catalog. So we have 2 different kinds of searches. First, we have the modeled searches. These all assume that our gravitational wave sources are compact binary coalescences. That means either a binary black hole, or BBH, a binary neutron star, BNS, or a neutron star black hole binary, which we call an NSBH. And each of these searches use banks of template waveforms that model the in-spiral, merger, and ring down of those compact objects and vary over the source's intrinsic parameters, so the masses and the spins. And we use those waveforms to filter the data and pull out signals that way. All of our modeled searches use any 2 or 3 detector combinations to form coincidences. And we additionally have GST-LAL, which allows for single detector candidates. Our last search is the minimally modeled search, CWB. CWB does not make any assumptions that our sources are CBCs, so it could in principle detect gravitational waves from many other interesting astrophysical sources. CWB also does not use matched filtering or waveforms. Instead, it identifies regions of excess power in the coincident strain data to find signals that way. And for this analysis, CWB used only 2 detector combinations to form coincidences. So it did not form 3 detector coincidences or include single detector candidates. Next slide, please. So now I just want to introduce a few of the numbers that you'll often hear discussed when we talk about the significance of our candidates. First is the false alarm rate, or the FAR. This number represents how often we would expect noise from our detectors to produce a trigger with the same ranking statistic as a candidate in question. And the false alarm rate does not include any astrophysical priors. On the other hand, we have the probability of astrophysical origin, or p-astro. And this number is calculated similarly to the false alarm rate, except here we include both the foreground or signal distribution of ranking statistics, as well as the background distribution. And the P-Astro includes information about our assumptions about astrophysical populations. So how often we would expect a given astrophysical event to occur will inform our estimate of the P-Astro. And this is the main number that we use as a threshold for inclusion in our catalog. So next slide, please. Now coming to our candidate list, we have our main events list, which includes 35 events passing a P-Astro threshold of 0.5. And since most of these events actually have P-Astro very close to 1, we actually find a pretty low contamination fraction of only 10 to 15%. Or in other words, we would expect maybe 4 to 6 out of these 35 events to be terrestrial in origin. But we, of course, can't tell which events those would be. We also publish a list of 7 marginal candidates. These are events which failed to meet that P-Astro threshold, but still had a false alarm rate of less than 2 per year. And finally, we release a deep subthreshold list of 1,041 candidates, which all failed to meet the previous 2 criteria, but still had a false alarm rate less than 2 per day. And so this subthreshold list, we expect to have a very low purity. We would expect only 20 to 25 out of these 1,000 events to be true astrophysical sources. But again, we can't distinguish which those would be. So again, I want to point out that all of these events come from the offline reanalysis of the data. So we do not include here any events which were found in low latency but subsequently retracted. And we also do not include events that were found in low latency but not found offline above the threshold. And so on the right, I've just shown a bit of a breakdown in how we go from that initial low latency public list to our final 35 events that we've now added to the catalog. Next slide, please. Here I show a visual representation of all of these events. So in the top, we have our 35 main events in blue. These are the ones which passed the P-Astro threshold of 0.5. And then the bottom row shows our 7 marginal candidates in green. These are the events which, again, did not pass the P-Astro threshold, but still had a false alarm rate less than 2 per year. Here, the thick black borders represent an event which was newly reported in our catalog for the first time. The pink boxes are for events which were only found in a single detector. And the orange borders show events which were subsequently found to be caused by an instrumental origin. So you'll notice down at the bottom in our marginal candidates list, we have 3 events which were found to be caused by instrumental origin. And each of these have had the GW prefix removed from the name. And this is just to indicate that we do not have confidence that these events arise from an astrophysical origin. Also in the marginal candidates list, we have GW200105. This is one of our previously published NSBH candidates. And although in our analysis, we did find this event with a slightly more significant false alarm rate than was originally published in the discovery paper, due to our uncertainties in the NSBH merger rates, we do find this event with a lower P-Astro than the threshold. And so we have to include it here as a marginal candidate. However, this is an event that we hope we can revisit later on once we've made more detections and we can reassess its significance at that time. So looking back up at the main events in blue, you'll notice that most of these are consistent with being binary black holes, which matches with our expectation. However, we do have 3 NSBH or potential NSBH candidates here. So first is GW191219. This is our most extreme mass ratio candidate. That means that while most of our other events have been sources with relatively equal masses and mass ratio close to 1. GW191219 has very unequal masses and a comparatively small mass ratio. And Isabel will talk a little bit more about this in the next section as well. But this extreme mass ratio makes GW191219 an outlier in its population. And since the P-astro depends on our assumed astrophysical populations, regions of the parameter space where we have few observations will be subject to greater uncertainty. And so we should keep this uncertainty in the P-astro in mind when it comes to GW191219. Moving on from this, we have GW200115. This is our other previously detected NSBH candidate. And this is our most highly confident NSBH candidate in this catalog. And finally, we have GW200210, which, as you can see, has an uncertain secondary component. So this component has a mass in the range where it may be a quite heavy neutron star, or it could be a very light black hole, but we can't tell with certainty what the true nature of this object is. And GW200210 is very similar to GW190814 from O3A. And regardless of the true nature of its source, it should be a very interesting event for further studies. So all in all, we've added many new events to our catalog, and everything we find is largely consistent with our expectations. So now I will hand it off to Isabel to discuss a bit more about the properties of these sources.
Thank you, Becca. Yes, so let's talk about the identities of the new binary compact objects that we've presented in GWTC3. So as Becca mentioned, we now have 90 binary compact object coalescence candidates with P-astro greater than 0.5. And the objects in these events are shown in blue and orange on this graphic, which shows compact objects that we know about in the universe, including those detected by the LIGO and Virgo detectors. So most of the events that we've seen with gravitational waves in all of our catalogs have been binary black holes. Some are binaries containing one black hole and one neutron star. And we've also seen two binaries in which both components are neutron stars. So in GWTC3, we present new confident binary black hole detections, some neutron star black hole binaries, and no new binary neutron stars. Next slide, please. So from these binaries, we detect gravitational waves like the one shown on this slide. And the signal contains information about the properties of the source, such as its masses, the way the two objects are spinning, and its distance from the Earth. And these properties are interesting, not just because we get to learn about these mysterious objects themselves, but also because their properties can contain hints about how these merging binaries actually form, which is not yet known, although we do have many theories. However, the signals are hidden in a lot of noise, so we have to carefully infer the most likely signal to produce the data. And we do this using Bayesian inference, which involves generating a lot of different waveform models under the assumption of different binary parameters, and then comparing them to the data. And there's more information about waveform models and waveform modeling in the GWTC 2.1 webinar if you're interested in that. So by doing this Bayesian inference, we get probability distributions for each of the describing parameters of the binary. And on the right-hand side of this slide, we have some posterior probability distributions for all of the events in GWTC3. You'll notice that there are quite a few of those. So for this webinar, I will be only focusing on a subset of these that I think illustrate some of the interesting features of this catalog. Next slide, please. Okay, so here are 9 events that I will highlight. So these violin plots are widest at the point of highest probability. And I'm showing the posterior probability distributions for the most massive binary component, which is called the primary, the least massive component, which is called the secondary, the effective in-spiral spin, which I will talk a bit more about in a moment, and the luminosity distance to the source. So starting from the top, GW191109 is interesting on 2 accounts. It seems to have negative effective spin. And what this means is that at least one of the binary components is spinning, and the overall angular momentum vector of the spin is aligned in the opposite direction to the angular momentum vector of the binary itself. So if only one of the components is spinning, then this anti-alignment can be demonstrated by the orange arrow in the diagram in the top left corner of this slide. And negatively aligned spins are rarer in our observations than negligible or positively aligned spins. GW191109 is also the second most massive binary black hole in O3b. The more massive binaries in our catalogue are quite interesting because they contain black holes that might have masses in a forbidden range of masses known as the pair instability mass gap, which is between about 60 and about 130 solar masses, where we should not get black holes forming through normal stellar evolution. And the fact that we do see black holes in this range indicates that our observed binaries might be forming through something other than normal stellar evolution, which I will talk a bit more about in a few slides' time. So moving to the next binary, GW191129 is the lowest mass confident binary black hole observed in O3b. GW191204 is confidently constrained to have positively aligned effective spin, which could be demonstrated by the green arrow in the top left. GW191219 and GW200115 are both binaries in which the lowest mass component is confidently thought to be a neutron star, but GW191219 is in italics due to the uncertainty on its P astro. And GW191219 has such an extreme mass ratio that it's outside of the range within which our waveform models are calibrated. So there may be some systematic uncertainties on the properties of this system. Although the two different kinds of waveform model that we use did actually agree quite well with each other. GW200129 is the most likely binary in O3b to have misaligned spins. This means that some component of the spin vector is lying in the plane of the binary orbit, as demonstrated by the purple arrow in the top left. GW200210 has an ambiguous secondary mass of about 3 solar masses. We do not know if this object is a neutron star or a black hole. GW200220 is the most massive binary black hole in O3b, again having masses that may be within this forbidden mass gap. And finally, for this slide, GW200225 also has significant support for negative effective spin. Next slide, please. The plot on this slide shows the 90% credible regions of the marginal posterior probability distributions for the primary and secondary masses of all neutron star black hole binary candidates detected by LIGO and Virgo. The intensity of the color represents the intensity of posterior probability support, and the straight gray lines are lines of constant mass ratio. Events that are plotted in color here are those for which we are confident that the secondary mass is a neutron star. And the events plotted in shades of gray are those that are a bit more ambiguous in that regard. So you can see here that GW191219, which is shown in green, has by far the most extreme mass ratio of this set, with a mass ratio of almost 1/30. And this system has a black hole with a mass that is very consistent actually with most of the most common black holes that we see in the rest of the population of about 30 solar masses. And a neutron star that is one of the lightest we've ever observed at about 1.1 solar masses. The other two neutron star black hole systems have lighter black holes and heavier neutron stars that are more typical of those that we see in electromagnetic observations. And we also have some candidates that are directly within this region outlined in green, where they might be black holes or neutron stars, since we don't yet know what the maximum mass of a neutron star is. Hopefully making more observations of neutron stars in the future will help to clarify where this region lies. Next slide, please. Okay, so this plot highlights those 9 events from O3b again, and also shows all other O3b events with gray contours. So the parameters plotted here are the chirp mass and the effective in-spiral spin, which are derived from the masses and spins of the binary components using the equations given in the top right of this slide. So the contours here show the 90% credible regions of the marginal posterior probability distributions for these two parameters. Most of the binaries are consistent with having 0 spin, although there are some events that strongly favor positively aligned spins. And there are also some events that are skewed towards negatively aligned spins. But overall, we find that these results are consistent with previous catalogs. Next slide, please. So for the next few slides, we're going to be looking at spin disk plots. So let's talk about how to read these. The left-hand semicircle in each plot shows the spin of the primary component, and the right-hand semicircle shows the spin of the secondary. Primary spins are always the better measured of the two, as the primary spin is more influential on the dynamics of the system. And in each semicircle, the intensity of the shading represents the posterior probability support. So the further away the support is from zero, the larger the spin magnitude, and the angle at which the support lies tells you the tilt of the spin vector, with 0 degrees being fully aligned and 180 degrees being fully anti-aligned. The event in the middle here, GW200115, is unusual in that the primary spin is leaning towards being negatively aligned, although it is also consistent with having 0 spin, just like our other NSBH observations. For systems with masses that are quite unbalanced, like these systems, we can also constrain the in-plane spin quite well, as you can see here. So why do we care about spins? Well, it turns out that we can use them to tell us about how these binaries actually formed. If the binary evolved from birth without any external influence, then we would expect to see aligned spins. So deviations from this tell us that binaries might be forming in other ways. For example, through dynamical assembly in densely populated environments like globular star clusters. Next slide, please. So these are some of the spin measurements for events in O3b that have these small positive spins. So these are consistent with being aligned, but they may have some slight tilt. And black holes are expected to have small spins if angular momentum transfer is efficient in stars when they expand during their evolution. But we do observe black holes in X-ray binaries that seem to be extremely rapidly spinning. So there is an interesting difference between the black holes that we see in gravitational waves and those that we see in X-rays. Next slide, please. So we also see some binary black holes with support for negatively aligned and misaligned spins. And these are not common, but we are seeing more of them as the catalog grows. One particularly interesting event is GW200129, which is shown in the middle plot. And the posterior support for this event is at very high spin magnitudes and almost completely in the plane of the orbit. So one way that misaligned and negatively aligned spins can occur is if the binary meets in a densely populated environment, for example, a star cluster, and undergoes frequent dynamical interactions that cause it to merge rapidly. Another interesting consequence of formation in a dense environment is that merger products may go on to merge again, which may also lead to observations of highly spinning black holes, since merger remnants should have a spin magnitude of about 0.7. And additionally, repeated mergers like this can give us black holes with masses in this forbidden mass range that I mentioned previously, between about 60 and about 130 solar masses. Next slide, please. So lastly, I will just highlight two events that are the most well localized. So being able to work out where the sources actually are in the universe involves triangulating the incoming signal using all observing detectors. So well localized signals are always the ones that are observed while all of the detectors are online. The best localized event in O3b is GW200208, which has been localized to an area that spans 30 degrees squared on the sky. So this looks very small in the plot at the top, but it's actually 150 times larger than the extent of the moon on the sky. We can also talk about the localization, the localized volume, which depends on the distance localization of the source to. And the most well-localized volume belongs to GW200202, which has a localized volume of 0.0024 gigaparsecs cubed. And this is the equivalent volume of about 10 to the 70 Olympic swimming pools. There are tens of thousands of galaxies in this volume, so we still can't really be sure in which one of these this binary formed and merged. Okay, thank you. I will hand over to Christopher now to talk about the data release and wrap up.
Thank you, Isabel. So I hope you've enjoyed hearing about all the science that we have done. Now, if we go to the next slide, you can see that we have a variety of data releases where you can try out this science at home. So if you want to start from our gravitational wave detector data directly, perhaps do your own searches or analysis, this is available from the Gravitational Wave Open Science Center. And if you'd like to use some of the data products we used ourselves, if you'd like to use the data quality inputs to the searches just described, or the Results of glitch subtraction, Jess also described that we use for parameter estimation. Those are available. The full candidate list down to the deep list, down to candidates of false alarm rates of 2 per day is available. The estimates of the search sensitivity, which are useful if you want to do any population inferences or to compare to your own search pipeline, are available. The parameter estimation results, as discussed by Isabel, and as well, all of the data behind our figures, as well as some scripts to reproduce those, are also available. Now, to summarize, from going on to the next slide, O3 saw the best ever performance of our detector network. Thanks to this, we've managed to get a large number of detections, and in O3B, we added 35 new candidates with p-astro greater than 0.5, as well as many other candidates with lower probabilities of being real. We now have a total catalogue of 90 candidates. These are a wide range of different sources, all binaries so far, but they have a range of different masses, spins, mass ratios, and we have now good examples of neutron star black hole candidates. Putting all these results together, we can do some really amazing work. And in upcoming webinars, we're going to discuss the implications for cosmology, astrophysics, and in the new year, tests of general relativity. Looking further ahead, we hope you're excited by our results so far. O4, our next observing run, will hopefully see even greater detector sensitivity and hence an even greater rate of detection. That's currently due to start in mid-December 2022, so around about a year from now, and that will hopefully see operation of both LIGO detectors, Virgo and KAGRA joining the network. So thank you very much. We will take some questions now. Please do use the Q&A box for these. So I think going first, there's a question, will instrument improvements in the detector give, detectors I think will give a large number of results in O3. And I think, Carl, maybe you would like to say something on this?
Chris, yeah, thanks very much for the question, Rohit. As we can see on this slide, the LIGO detector is expecting to increase their sensitivity from 140 megaparsecs to 190 megaparsecs. So the number of events we expect to detect increases with the volume of space we're searching. So it's the cube of the distance. And so we might expect to detect 2.5 times as many events in the next run, assuming we search for the same amount of time that we searched as this run. So I hope that answers your question.
Cool. Thank you, Carl. There was also a question on vacuum squeezing. So perhaps you could add a little bit, Carl, a bit more about how vacuum squeezing helps with the uncertainty principle.
Yeah, so this is exactly right. The vacuum squeezing is a way to use the Heisenberg uncertainty principle to our advantage. So the Heisenberg uncertainty principle says that there's, if we try and measure two things, there's a minimum amount of noise we can have in the product of those two things. But a gravitational wave detector only cares about one thing. And so we can squeeze the noise all into the thing we don't care about, the thing that doesn't detect gravitational waves, and have a very small noise in the thing we care about, the thing that detects gravitational waves. So you would have seen a plot of a circle in Francisco's slides, and that circle squeezing stretches out that circle, and saying we're measuring a reduced noise in the squashed part of that ellipse.
Thank you, Carl. We have a question of any sign of lensing in the latest data. I'm assuming this is greater gravitational wave lensing. So our analysis of O3B is still currently underway, so we can't show you the results of that yet, but hopefully we will have some answers for you soon. And I think someone can point you to the results in the chat about for O3A. We have a question, is there a confirmed candidate mass within the forbidden mass region? So I'm assuming here you mean one of the mass gaps. We potentially have two mass gaps, the lower mass gap and between neutron stars and black holes, where we have a couple of candidates, and also at the upper mass gap, the pair instability mass gap. So I hope Isabel will be able to say a little bit more about that. Isabel, do you want to take over?
Sure. So yes, on this plot, we can see the lower mass gap, where we can see that there is a candidate directly within that mass gap where the 90% credible region is not extending outside of there at all. And that is 190814. And actually this lower mass gap is kind of thought to go anywhere up until 5 solar masses potentially. So the lighter gray event GW200210 also seems to be within this mass gap for the secondary mass. In terms of the upper mass gap, we do have some candidates that are in that mass gap as well. For example, in previous catalogs, GW190521, its primary mass was well within this mass gap and didn't really stray outside of that at very high confidence. We can see here that our chirp masses are fairly high. It's difficult to kind of locate where the mass gap is on the chirp mass plot though, because the chirp mass is kind of a combination of the two different masses, but a couple of the masses in this catalog as well could be within that upper mass gap.
Thank you very much, Isabel. We have another question on O4 sensitivity and the potential of being able to detect binaries pre-merger. So this is a data analysis problem and a low frequency sensitivity. As that improves, that makes a bit better. Becca, perhaps you might be able to say a little bit more on this.
Sure. So basically, the answer is that this pre-merger detection or early warning detection is something that's a current area of development for our pipelines. And we are hoping to be able to achieve this for O4. And I think that the increased detector sensitivity will definitely be something that helps us in O4 to be able to accumulate enough SNR in the signal pre-merger to be able to find detections early that way. So hopefully that answers the question a little bit.
Cool. Thank you. We have a question on how many of the catalog counterparts are accompanied with electromagnetic counterparts. So I think Rosa can say a little bit more about the latest results here.
Yes, there are no confirmed electromagnetic counterparts for any candidates in O3B catalog so far.
Okay, simple answer there. Of course, we don't expect counterparts for the binary black holes. The neutron star black holes also don't often have an electromagnetic counterpart, so that's a bit difficult. Looking further back, we have GW170817, a binary neutron star in O2, which did have a nice counterpart. Okay, we have another question on current detector sensitivities detect primordial gravitational waves. That's on stochastic backgrounds. That's a different source there. So I think if you can watch out for future webinars on other sources, we'll get to that. Okay. We have a question on why does the glitch rate increase compared with O2? Perhaps Sid would like to say a little something about sources of noise in O3.
Yes, so as we become more and more sensitive, we also become more and more sensitive to noise. So our sensitivity was higher in O3 compared to O2. And that's why we became more sensitive to noise. We were also able to stay in the locked configuration in O3 for longer times, and that also increases the glitch rate.
So I think it's one of the costs of having improved detector sensitivity is we also are more sensitive to new sources of noise. Okay, we have a question on KAGRA's sensitivity is still being quite low. We're hoping that there will be a large improvement in O4 in their sensitivity over the course of the run. Of course, we won't know exactly how that will happen until we manage to achieve it. So we'll have to wait and see on that. It potentially, even if the detectors are not sensitive to make independent detections, their data can still be very useful for confirming the localization of the source. And we saw this back in 2002 with the case of GW170817, which was not detected by Virgo, but could have been detected by Virgo if it was in the right position on the sky. So by virtue of the fact that it wasn't detected, we were able to constrain some things there. So over time, KAGRA will get up to more sensitivity, and then in future runs beyond 04, we hope that they will all be quite comparable to with each other. Okay, so I think we have one more question in the chat that I want to address, so not in the Q&A, but asking about sources of information about how we do our analysis and where to learn more. And I'd recommend visiting the Gravitational Wave Open Science Center and looking for the Open Data Workshops. These are events held every so often where you can sign up and go through some tutorials on how to analyze the data from detector characterization through searches to parameter estimation. You can also go back and review past workshops and see recordings of lectures and find some examples of things there. So that's an excellent resource if you want to get started with our data and understand things there. So that's a good question. Okay, we maybe have time for a couple more questions. We have a question on how we measure spins of black holes. So I think Isabel already covered a little bit about how we do the general inferences. But perhaps Sergey would like to say a little bit something about how the effects of spin influence the signal and what we look for in order to measure these properties.
Yeah, so spin comes in several different ways. The primary way that it comes in is this effective spin that we talked about that makes the waveform shorter or longer, all other things being equal. So that affects the phasing and how long the waveform is. And then the other components of the spin, which are lie in the orbital plane, cause the orbital plane to precess, which encodes both modulations in the amplitude and the phase. So they come in different ways. For highly unequal masses, the primary spin is the most important, but of course, close to equal masses, both of them play a role.
Thank you, Sergey. So if there are no more questions in the chat, I think I'll just wrap up with one, which is, Jess, could you introduce us to your cat, please?
Oh, I would love to. I think she takes every opportunity that she can to be famous. So you saw Shiva the science cat helping us out today. Yes, she's, I think, curled up somewhere warm right now. It's snowing here in Vancouver.
Okay. Excellent. Thank you very much. And with that, we're at the end of the hour. So thank you, everyone, for attending. We'll close up the questions here. And a recording of this should be put on YouTube for future reference. So thank you very much.